Hi everyone, and welcome to your last video for AP Calculus, unless I guess we decide to make some videos for review, but most likely this is your last video. And what we're going to go through today are some FRQs from old AP tests that involve area and volume. And so we're just going to go through these so you kind of see what these problems would look like. So the first one you can see right away, we've got a table. It gives us the height in feet and then the area in square feet. So we have a tank that has a height of 10 feet. The area of the horizontal cross sections of the tank are given by the function A. So that's what you see in this table. Those are at each of those heights what the area of that cross section would be. It tells us the function A is continuous and decreases as h increases, and then select values for the area of those cross sections are given in the table. So for number one, it says use a left Riemann sum with the intervals indicated by the data in the table to approximate the volume of the tank. So the idea here, it's kind of like what we did with cross sections when we were slicing. We knew if that we could add up those cross sections, we could get the volume, and we use integrals to add those up. Well, in this case, we don't have a function, but we have a table, so we can use the Riemann sum to approximate the value of that integral. So it says a left Riemann sum. So we're going to go from 0 to 2, 2 to 5, and 5 to 10 are my three subintervals given by that table. And then, let's see, left. So at 0, the area is 50.3. At 2, it's 14.4. And 5 is 6.5. So then we're going to do base times height because we know these are rectangular approximations. So I have 2 times 50.3 plus 3 times 14.4 and then plus 5 times 6.5. And this question is a calculator question, so we'll go ahead and use our calculators here. Still haven't put batteries in, so hopefully it's not going to die. Okay, and I get 176.3 for my value. Now, we've got to think about the units because it says to indicate the units of measure. So for my base here, I know that was measured in feet. And my height was measured in square feet. So since we're multiplying feet by square feet, so that's going to give me 176.3 cubic feet. And that would be the approximate volume of the tank. So now part B asks if that approximation from part A is an over or underestimate of the volume. So here's what we need to consider. They're telling us that the function A is continuous and it decreases. So we know that function is doing something like this. It's decreasing. Now if I do a left approximation, you can see that those rectangles overestimate the area. So we would say the approximation is an overestimate because A is decreasing and a left Riemann sum is used. And again, this is not something that I try to memorize. I always just go to a sketch so I can quickly determine whether that's an over or underestimate. Alright, so now part C says the area in square feet of the horizontal cross section at height h feet is modeled by this function. So that's giving me the area of each cross section. And they're asking us to find the volume of the tank. Now again, if I know the area of the cross sections, all I need to do is add up all of those cross sections, and we do that using an integral. So my volume would be the integral. Now height, we know, let's see, the height is between 0 and 10 because the height is 10. And I'm going to add up all those cross sections that are represented by f of h. And then I need my dH. And I'm going to use my calculator to figure that out. So again, we're just using the integral to add up all those areas, which will give us a volume. So let's see, this was 50.3 over e to the 0.2x plus x and then dx. So remember, we're always going to 3 decimal places. So we get 101, there's a glare there, 101.325. And again, my units would be cubic feet. And you can see here the actual volume is actually less than our estimate, which supports what we said here, that approximation was an overestimate. All right, so now the last part here. Water is pumped into the tank. So when the height of the water is 5 feet, the height is increasing at the rate of 0.26 feet per minute. And then we're using this function from part C. It's asking us to find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet. Now, hopefully when you saw this, so the rate at which the volume of water is changing with respect to time, we should be thinking related rates. So here's what we need to do. So I'm asked to find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. So the first thing I need to do is relate the volume to the height. So now we know from part C, we found the volume of this tank by integrating our function f of h, right, by adding all those cross sections. So the volume is the integral from 0 to h. I'm going to call this f of x dx. So that's my function. If I integrate my f of h, then I'm going to get the volume. Now, I want to find the rate at which the volume is changing. So I'm looking for dv dt. So that means I need to differentiate with respect to t. So the first thing I do is just take the derivative of the right-hand side. And here's where we're going to use the fundamental theorem. If I differentiate this side, the derivative of the integral is just going to give me f of h. Now, because I'm differentiating with respect to t, and this function has an h in it, that's where we need that implicit piece, and we're going to include our dh dt. So now, to solve this problem, it looks like I've got a dv dt, there's an h, and I've got dh dt. So I need to figure out what's my unknown and what pieces do I know. So when I go back, we're looking when the height of the water is 5 feet. So we're doing this when h is 5. It says the height is increasing at the rate of 0.26 feet per minute. Since that's increasing, I have a positive rate, so my dh dt is 0.26. And we were asked to find the rate at which the volume of water is changing, so dv dt is our unknown. So our last step now is just to plug it in. So we're looking for dv dt when the height is 5. That's going to be equal to f of 5, and I'll use my calculator to figure that out. And then dh dt, we said it was 0.26. So we're going to go ahead and calculate this out. So let's see, f of 5, I have alpha y equal 50.3 over e to the 0.2 times 5 plus 5, and I'm going to multiply that by 0.26. Sorry, you couldn't see any of that. So there's how I entered it, and my answer is going to be 1.694. Now, we're talking about the rate at which the volume is changing. So that's going to be cubic feet per, and our time is in minutes here, cubic feet per minute. So you can see how even though this started off as a volume problem, right, they pulled in some related rates here. All right, let's look at the next page. All right, so now it says let R be the region bounded by the x-axis, the graph of y equals the square root of x, and the line x equals 4. So first thing we're going to do is sketch a graph. And I believe this would be no calculator. Probably really good at sketching square root of x by now. Looks like that. So I'm bounded by the x-axis. So down here, the function, and then x equals 4. So I'm trying to find the area of this region here. So since I notice my top always stays the same. I only have one bottom. I'm going to do this with respect to x. I'm going to use top minus bottom. So my area is going to be the integral. My x values go from 0 to 4. I have the top is the square root of x, minus the bottom is 0, and then dx. So really what I'm trying to find is the integral from 0 to 4 of the square root of x dx. So now, since this is without a calculator, I need to anti-differentiate this. If it helps you, right, we can write this from 0 to 4 of x to the 1/2 dx. So my antiderivative, if I add 1 to the exponent, I get x to the 3/2. I need to divide by that new exponent, which is the same thing as multiplying by the reciprocal. Then I have my plus c, and I'm evaluating from 0 to 4. So if I plug in my 4 for x, I can take the square root, which is 2. 2 cubed is 8, so I get 16/3 plus c. And then I'm going to subtract. Well, if I plug in 0, I just get 0 plus c. So the area would be 16/3. All right, now here's a little different type question. So now it's telling us that there's a vertical line, x equals h, which divides the region R into two regions with equal areas. So if you can imagine some hypothetical line, x equals h. And it's dividing that such that we get two equal areas. So it doesn't actually seem likely that that would be the right location of the line. But what it's asking us to do is write but not solve an equation involving integral expressions whose solution gives the value h. So there's two ways we could do this. If I know that integrating up to this line gives me half an area, or half of this total area, I could say that the integral from 0 to h, I'm still doing top minus bottom, which was square root of x, dx. If I integrated from 0 to h, it should give me half this area. So I could say equals 8/3. That's one way of doing it, because if it's the same area, I should half of the area on each side. Or I could say that the integral from 0 to h of square root of x dx should be equal then to the integral from h of h to 4 of square root of x dx. So in other words, integrating from 0 to h and integrating from h to 4 should give me the same areas. So those are two possible answers. Either one would be acceptable. All right, let's look at part C. Now, part C is asking the volume of the solid generated when R is revolved about the x-axis. So again, we've got the same region. We're still with respect to x because we're revolving about the x-axis. So I'm going to highlight that here. Okay, it's the same region bounded by our vertical line x equals 4. So here's our region. And you can notice here, because that region butts all the way up to that axis of revolution, we're not going to have any holes. So we're just going to have one radius. Our radius is going to be top minus bottom which is going to be the square root of x minus 0, or just the square root of x. So now, to find the volume, we know it's pi r squared because we're adding up all those circular cross sections. So I'm going to have pi times the integral from 0 to 4. I've got my radius squared, square root of x squared, right? This is our r, dx, which is the integral of pi from 0 to 4 of x dx. So I'm going to find the antiderivative. I get x squared over 2 plus c, integrating from 0 to 4. Actually, I'm going to put this up here because I'm going to run out of room. So now if I plug in 4 squared is 16 divided by 2 is 8. So I have pi 8 plus c minus, well now if I plug in 0, I'm just going to get 0 plus c. So my c's cancel out and I just have 8 pi is my volume. All right, so the last piece, the vertical line x equals k. So again, we've got this idea of a vertical line. In this case, it divides the region R into two regions such that when those regions are revolved, they generate solids with equal volumes. So again, if I had x equals k, it means that revolving this region and revolving this region will give me equal volumes. So again, we're asked to write but not solve an equation involving integral expressions whose solution gives the value of k. So this is very similar to part B. The idea here, right, our radius is still our top minus bottom, but the idea is that finding the volume from 0 to k, right, our r squared is square root of x squared dx, so that's my pi r squared. I'm adding up all those areas. That should be 1/2 of the total volume, or 4 pi. Now, just like the top, I could write this in one of two ways. Or I could say that integrating from 0 to k should give me the same volume as if I integrate from k to 4 of square root of x squared dx. So again, either of those two answers would be acceptable. All right, that's it for this last video. Your practice in class will be going through lots more AP questions to make sure we've got how this works. All right, make sure you've got good notes. I will see you back in class. Thanks.